Okay, this lecture is on the functional groups of our organic chemistry unit, and I am going through our PowerPoint presentation or our Google presentation that is actually on your website right now. So I am clicking through this, and you certainly can go back and look at this in closer detail if you see something that, or you can't see something that I'm doing here. So I'm going through the functional groups. You really should have reference table R out to show you that. Okay, so in any case, functional groups, as I talked about today, are nothing more than an arrangement of hydrocarbons that have some unique type of functional group or types of atoms in a certain arrangement attached to the carbon chain that gives them unique properties. Okay, and table R is basically what I'm giving you here in this worksheet here. Table R shows you the class of the compounds, the functional group, that's what's actually attaching to the hydrocarbon chain, its general formula, which R means usually the rest of an organic molecule, with what it's attaching, which is that X. The X in this case is the functional group. And really important, they give you in this table how to name these compounds. They give an example of how they name them. Now we've done halocarbons already when I was naming alkanes. So this is our first hydrocarbon. We've also were adding methyls and ethyl groups, and if you notice, those are just hydrocarbons with attachment groups that are hydrocarbons, so they don't actually have any new classes. So we're going to add things that are not hydrocarbons to our carbon chain, and we call these functional groups because they tend to have a unique set of properties that are very similar to each other. In any case, the halocarbons are first, and we'll begin that way. All right, so next slide. This is just flipping down through our table R here, and there's alcohol, ethers, aldehyde, ketones, organic acids, esters, amines, and amides. Notice these are the actual functional groups that are either inside a hydrocarbon or at the end. And here is the formula. R is the rest of an organic compound. Notice an ether is on either side of different carbons. Okay, so you can think of these R's as carbons, but they can also be a hydrogen in its most simplistic case for like the aldehydes. Any case, the examples of each are given. So think with me. You have an example of what it looks like, an example how to name it, its basic general formula, and the actual attachment group for each of these. So it's a lot of information here. Okay, and we're going to go through these pretty quickly, but again, you have this as a reference point. Okay, so moving on, okay, we're starting with the halocarbons, and these are particularly important types of compounds that we've used forever in terms of refrigerants, and they have the general form of RX, RX being either a chlorine, a bromine, a fluorine, or an iodine. Okay, in any case, down here we have some examples of naming them. 3-carbon compound is a prop. We have a chlorine in the first one, so if you click, okay, not like I just did. If I click here, I guess I didn't put them there. This, of course, would be a propane with a chlorine, so 1-chloropropane. This one right here is 3 chlorines. It's also propane, but I have a double bond, so this is 1-propene. On the second carbon, I've got a bromide, so 2-bromo, 1-propene. And this one is a methyl. This is like we've already talked about. This is not a halocarbon. Okay, that's just what we have. So we have a methyl in the second, so 2-methyl a pentene, pen for 5 carbons. All right, a little bit of review there. Okay, so I've got my Freon. Okay, and again, the common uses I have up here you can read, and there's so many types of them. They're important solvents, refrigerants. We've used these as aerosols forever. Pressurized, an aerosol basically is a compound that we use to push out of the products, like if you have hairspray or if you're trying to push out shaving cream. An aerosol is that gas under pressure. And if you notice, looking at the reaction, these chlorocarbons, okay, sometimes called chlorofluorocarbons, are dangerous to our important O3 layer called ozone, because in light, okay, ultraviolet light, okay, what we do here, Planck's constant times frequency, is energy of light, right? So high energy photons will split the chlorine off this this radical chlorine. Now, chlorine likes to become Cl2, so this is a radical chlorine with one dot, one electron, or with, I would just say, seven valence electrons, okay, badly reacts, very reactive, and it's going to basically pull an O off and make O2, and this is how it depletes the ozone. Now, this intermediate that's made reacts with more ozone to make what? More radical chlorine that does what? Restarts the process. So one of these chlorofluorocarbons, okay, these carbon-based materials, okay, can continue this cycle for many thousands of times. So only a little bit in the ozone later can have catastrophic effects, and we've lowered the use of this worldwide, internationally, and supposedly we've helped reestablish some of the ozone that was depleted, okay, in the 70s and 80s when these chemicals proliferated our atmospheres, okay. Some things you should also know. In any case, we have something called 1112 tetrafluoroethane. This is another compound that we now use instead of chlorofluorocarbons. And notice fluorine to chlorine is going to be a much stronger bond, so these fluorines don't slough off and attack the oxygen. Okay, so this is, if you read your dust off, or it's a very, very common propellant or aerosol. And DDT, its name is Dichlorodiphenyltrichloroethane. Okay, molecule, very nonpolar, very symmetrical. Okay, was used as an insecticide, but because being so nonpolar, it got into the animals up the food chains of the insects, of the rodents who ate it and so forth, and stayed in their bodies. And the bald eagles almost became extinct because of their inability to lay eggs because of this chemical. All right, so there's some history behind halocarbons. All right, alcohols. Alcohol is the product of fermentation. It's been around for thousands of years. Okay, I don't know if beer was first done with the Chinese, maybe, not really sure. But any case, fermenting alcohols and grains. Alcohols are not bases. You see this OH group, but this R means the rest of an organic compound, meaning carbons and hydrogens. So if you have an OH here, so this is 1-propanol, okay, and this is 2-propanol. Why is it 1-propanol? Because on the first carbon you have an OH group, 2-propanol, okay, the OH group is on the second carbon, so these are isomers, okay. And moving forward, all right, okay, 1-propanol, 2-propanol, okay, as I had there. And then, of course, we have methanol, methyl alcohol, methane. You take the E away, add OL. And I'm adding OL. And again, for those that are saying, how do I know to add OL? Going back to table R here for alcohols, look at the example they gave you. They give you 1-propanol. So they give an example. You add OL. So you add OL after you take the E away. That's all I'm doing, guys. I'm just looking at this table. And if you have table R open, it can be very helpful to see how we name these. So getting forward here, all right, this is methane with an OH group, so it's methanol, okay? Let's go back. This is ethyl alcohol. This is the alcohol that's made from the fermenting of wine or liquor. This is ethanol, okay? Oops, and I guess I didn't put it there. Ethanol. Okay, so glycerol. Okay, the glycerol is 1, 2, 3 of these OH groups, so this is going to be a triol, okay? And again, let me go back. The IUPAC name of ethylene glycol is 1,2-ethanediol. Notice the 1, 2, eth means 2 carbons, ethane is single bonds, and the diol is for the 2 OH groups. So glycerol is going to be 1, 2, 3 propantriol, right? 1, 2, 3. Okay, prop because there's 3 carbons, ane because there's single bonds, and triol, kind of like that when we had a double bond, we had dienes, but triol. Since the OL is the alcohol, we have 3 of them. This is 1-propanol, 2-propanol, second carbon, the OH group. This is meth-eth-prop-bute, and that carbon's on the OH is on the second carbon. We always choose the slowest number, not the third, so 2-butanol. And this one, 1, 2, 3, is a longest continuous chain, so it's a propane, single bonds, propanol, but on the second carbon, we've got an OH group, and the second carbon, we've got a methyl group. So it's a methyl, or 2-methyl, 2-propanol. Remember, a number is needed for each attaching group. Okay, aldehydes. Okay, these special compounds are an ending group. Okay, the R at the end means the rest of an organic compound. This is a CHO at the end. Sometimes I call it the CHO group, CHO mama group, CHO. Okay, so they're always an ending group, and they're made by the oxidation of alcohols. Alcohols eventually get oxidized, become these aldehydes. Now, aldehydes, most famous of all is this one right here called formaldehyde. It's used to prevent decay of organic tissue. Cadavers have been long been preserved, okay, by formaldehyde, although now it's considered to be a carcinogen, so it's not used anymore. But formaldehyde is a common name of this guy right here, and the simplistic name is a meth. There's no double bond, so methane, but to end an aldehyde, we use the AL ending, so methanol. So formaldehyde is methanol. This is ethanol. Notice the difference. This is not an OH, it's a C double bond to an O to an H, so a different functional group. Okay? And some more information here. Acetaldehyde is meth, look at the CHO, CHO means you have the C double bond to an O to the H at the end of a molecule. That's why there's no numbers associated, because aldehydes are always at the end. And of course, this is ethanol. All right. Cinnamonaldehyde is also an aldehyde, okay? And then the actual IUPAC name, you're not responsible. It's some kind of phenyl group, but I have to look that up. There's also a ene in here, so some stuff going on. But look at the CHO at the end, CHO. Okay, ketones are also much like aldehydes. You have a carbon double bond to an O, but an aldehyde is a carbon double bond to an O at the end. Now look at the general formula that's given to you in your reference table, R and R prime. This means you have the rest of an organic molecule on this side and the rest of another hydrocarbon chain on this side. So it's the middle group. So this is basically an aldehyde in the middle. And if aldehydes are made from the oxidation of alcohols, okay, well, this is the oxidation of alcohols as well, except the alcohols are different. Okay, let me explain that. This is called a primary alcohol, where an alcohol, the OH group, is at, well, the OH is attached to a carbon that's only attached to one other carbon. So this is a primary alcohol. Okay, now when it gets oxidized, okay, redox, it becomes an aldehyde. Now, if I have a secondary alcohol, this is an OH group that is attached to a carbon that's attached to two other carbons. See, this carbon here was only attached to one other carbon, so this was a primary. This is called a secondary. Now, this is attached to the middle. Now, you oxidize this, it becomes a ketone, where you have an O double bond to an O, but in the middle of a hydrocarbon. Okay, and there's also called tertiary, okay, alcohols, and you've guessed it, the middle carbon is attached to 3 carbons, and here's an example of a tertiary, okay, hydrocarbon, okay, where this carbon is attached to 1, 2, or 3. Okay, so that's where that stuff comes from. So if you oxidize alcohols, OH groups, okay, they become either an aldehyde, CHO mama group at the end, or they become a ketone, which is really the same thing. A carbon double bonded to an O, instead of being at the end, okay, is in the middle. All right. So I guess I'm not pausing. Any case, back to here, how do we name these ketones? They add an "one." So this is meth, eth, prop. Prop-one sounds weird, so we add an A in there for propanone. But where is the ketone located? On the middle carbon. So we call this 2-propanone, which, by the way, is called acetone, which is used for all different types of solvents. Very important organic solvent. This thing's going to dissolve a lot of things. We know acetone can degrade many products, especially nail polish. Okay, so in any case, this one is meth, eth, prop, bute, pent, pentane, pentanone. Where is it? On the lowest carbon possible, so 3. Okay, 3-pentanone. By the way, acetone or 2-propanone, that should look familiar to you. Remember table H? That's where we talked about what? High vapor pressure. And who has high vapor pressure? Organic molecules, propanone or 1-propanone. Or, okay, in this case I should say 2-propanone, but sometimes you don't use numbers because propanone is the smallest type of organic ketone that we have, because the middle carbon, okay, is a carbon double bonded to an O. Therefore, if it has to be a middle, we don't need any numbers. So 2-propanone or propanone, but this is acetone. And we notice this is the one that what? Vaporized the easiest. It had the weakest attractive forces, and it was the most organic of the group here. Ethanol, whoa, wait, is this? Ethanol has an OH group with 2 C's. So we're seeing that these guys are starting to make some sense. I can give you propanone, and you better explain to, hey, that's 3 carbons, single bonded with an ON group in the middle. Okay, ethanol, 2 carbons, single bonded ane. The OL means it's an OH group. Ethanoic acid is coming soon to a party near you. Okay, so back to where we were. We were at ketone land, so let's get there. Then what happened to me? So let's go back to ketones, and we had our propanone or 2-propanone. Again, you don't need a second number because the only way for this to be a middle group, this has to be in the middle. So propanone doesn't need a number. Of course, this one does, 3-pentanone. Okay, moving forward. Ketones. Okay, the interior of molecules, and thereby the oxidation of secondary alcohols, like I showed you before. Okay, and ethers. Okay, ethers. All right, ethers have a long history of use. Okay, in medicine, they were the first form of anesthetic in terms of knocking patients out. So anesthesiology got its beginnings with using ether. There was an important, it was a movie that 10 years ago called Cider House Rules, the use of ether. Any case, ether, I remember, is on either side. Notice it's not a carbon double bonded to an O like a ketone or an aldehyde. It's on either side of an organic molecule. You've got these C's. So when we name these, and again, you have the example in table R, you name the carbon chains around them. This is an ethyl group. This is an ethyl group. So notice it's diethyl ether on both sides. This has an ether on one side and has a methyl group. So this would be a methyl ethyl ether. Methyl ethyl ether. Okay? And I believe this is the one that was used, okay, to knock patients out. Okay? And again, one way to make ethers is put 2 alcohols together, take out the water. Taking out the water is called dehydration, and you push these 2 carbon chains together, called dehydration synthesis. Okay, so moving forward, so diethyl ether, okay, I'm sorry, the diethyl ether was the one used in hospitals, so diethyl. Okay, and we have the vanilla molecule. Okay, so if we take the molecule of the vanilla, whether it comes from the root or we make it in a laboratory, it's essentially the same molecule. Some people go to the restaurant, to the food store, and say, I have to have the vanilla extract, or I'll buy the synthetic for half the price. Well, just on the chemistry set, it's the same molecule whether you make it synthetically or you make it, or the nature makes it. However, when nature makes it, there's other molecules associated with, I think, that the people are talking about. Who knows? But anyway, the OH group here is going to be the alcohol. The OCH3, where you have a CH3, and this is a carbon chain around it, would be, you've guessed it, the ether part, right? On either side, there's a carbon chain. Don't forget this ring has a carbon in it. And look at this, a carbon double bond to the O at the end of a molecule. That's that aldehyde. Okay, and again, if you didn't know these, you use the general formulas from table R, and you'd work it out, as the Beatles would say. Okay, moving forward. Acids. This is by far the most important of all the groups. They pick on this one. Of all of your functional groups, this is the only one that is a electrolyte. It's the only one. Why? Because it will slough off an H. Now people say, well, why does it do that? It does so because this O and this O, okay, are resonating. So if these electrons can resonate back through the carbon, it makes the conjugate base of an acid very stable. So an organic acid has this functional group R and this C double bond to an O, kind of like a ketone, kind of like an aldehyde. It's at the end like an aldehyde, but it has this like alcohol group attached to it. So it's like a aldehyde with an alcohol. But this H can be sloughed off to make C double bonded to an O to O minus, okay, and this H plus. Now, this electron, or this negative, okay, can jump back here and push this one out, make this one the negative. And we can have this scenario. And these resonate back and forth to make this stable. And if your conjugate base is stable and can exist, that means the H plus can go. And if you don't like that, these two oxygens do what? They pull on the pair of electrons that's bonded to the H this way and drift them so that the H plus can slough off. These are weak acids. Okay, vinegar, as we like to say, okay, is acetic acid, but it's an organic acid. CH3COOH, okay, is called a Cu group. So organic acids are denoted by the Cu. Okay, notice the aldehydes are the CHO. So this is the Cu group, and you've got two O's in the end and an H. And this H can come off and make protons or make ions, and a conjugate base is left that also gives off ions. So therefore, these guys are your electrolytes. These are the only organic electrolytes. What's an electrolyte? Acids, bases, okay, and salts. Well, this is a weak acid. All of our weak acids, citric acid, okay, ascorbic acid, vitamin C, all our acids of our body, okay, are going to have carboxylic acids endings. You guys learned in biology last year. What was a fatty acid? A fatty acid was a long hydrocarbon with a, guess what, a carboxylic acid ending, or a Cu group ending. Okay, how do we name them? Very simply, we count the number of carbons. Okay, I'm giving you an example here. So this is an example of an organic acid. So this would be propane, take the E away, oic acid. That's it. We don't name where this is because it's always at the end. Okay? So this is formic acid, otherwise called methanoic acid. This is ethanoic acid. This is butanoic acid. Okay? And of course, this is a diprotic acid here. Okay, oxalic acid, which is a find in plants and rhubarb. You guys used oxalic acid in AP Bio when you titrated with potassium permanganate. Okay, moving forward. Okay, now you can make these acids by oxidizing alcohols. I told you before, if you take an aldehyde, if you take an alcohol and you oxidize it, you can make a ketone, or you can make a what? An aldehyde. If you keep the process going and keep oxidizing, eventually an aldehyde, an ending primary alcohol, will become a carboxylic acid. And we know this to be true. If you read this here, we know that vinegar, okay, when it's exposed to oxygen, okay, will make the aldehyde and eventually make vinegar and give a vinegar taste. So it's wine that has been exposed to oxygen. The alcohol, the ethanoic acid that we got from fermentation, the ethanol we got from fermentation would become an aldehyde first because this is a primary alcohol, and then eventually into an organic acid. Okay? Any case, which of the following compounds is not a base? Well, we know a metal and a polyatomic ion is a base, metal polyatomic ion. Ammonia, although not an Arrhenius base, reacts with a water to pull an H away because it's got a lone pair. Okay, it's a Bronson-Lowry base. It's a hydrogen acceptor. This is not a base. Okay, why? Let's see if I'm right. It's not a base because it is an alcohol. This OH does not slough off. Okay, amines. Okay, amines are nitrogens that have, if you guessed it, carbons surrounding them. Okay, and There's a bunch of them. Ammonia is an amine, although you don't see carbons, they use the hydrogens there, so sometimes that R could be considered for just an H. All right. This is methylamine, methyl attached to the N. And of course we have phenylamine, which the phenyl is a benzene ring, not part of the course. Okay. Many uses for amines, but the more notorious uses of what you hear about, I wouldn't say it's the important use, is the drugs, amphetamines. Amphetamines, okay, so these are stimulants. This is probably the most used amphetamine in the world. If you don't know what this is caffeine. Okay, notice the N is attaching to other carbons. Notice the amines here. Another one, okay, that's also used, but I think it's going down in use. It's so expensive. Nicotine. Okay, and there's a bunch of others. Okay, so amines are stimulants. They're also bases because of the lone pair they can accept H's, and they're used again for medicine, dyes, and all different types of things. Okay, so the organic bases are your amines. Okay, here's some other ones. When you decay, this is when you decay. This is when you don't want to smell, and this is cadaverine. Okay, this is what's rotten flesh looks like, and it's got that ammonium ending, and this is what rotten fish smells has. And by the way, this up and down is the carbon. So this is a carbon here, carbon here, carbon here. Notice the up and down to show the tetrahedral effect. Putrescine is the smell of rotten fish, and these are also very poor, terrible smelling compounds that amines are also known for. Okay, amides are a little different. Amides, okay, are ends attached to a carbon with a double bond, as table R shows us. Okay, and again, here's an example of amide formation. You take an organic acid, notice this is a carbon, the Cu group, plus an amine. Okay, the water comes out, and you make an amide. So an amide is you have that amine, the end bonded to stuff, attached to a carbon with double bond. Again, if you don't know this, look at table. Table R is telling us clearly that an amide has a carbon double bond to an O to an NH. Okay, and here's an example. Okay, so those are you just have to pay attention of what you're talking about, the amine or amide. Of course, amino acids. Okay, if you think with that, you're taking an amine here and attaching with a carboxylic acid. Water is coming out, dehydration, synthesis, and be making something called a polymer. Okay, this would be a condensation polymerization, taking water out, as we'll talk about in part 3 of this lovely tour. Okay, in any case, that is amino acids. And now we have the last one, which is the most difficult to name, is the esters. Okay, esters are named or basically known for being very aromatic, sweet smells of nature, whereas amines, okay, we're smelling, the esters are the sweet smelling. So flowers, fragrances, perfumes are all made from the esters. Okay, now esters have this kind of shape to them. They have a kind of a ketone idea and then an O in the middle. So it's kind of like a carboxylic acid in the middle. Okay, but C double bonded to an O here. Now we name esters by how they're made. And let me explain. If I take an alcohol, this is 2-carbon alcohol, and I take butanoic acid, remember this is a carbon, this is a carbon, this is a carbon, this is a carbon for 4, and you push them together and water comes out, that's where that should be, water. You push them together and we name them by calling the alcohol part that makes them the ethyl group and the acid group the butanoate group. So there is ethyl butanoate, of course that's water, okay, and believe it or not, that's the smell of pineapple, ethyl butanoate, okay, or the taste of pineapple as well. Now, look at this compound, 1, 2, 3, 4, so 4 carbons. This is butanoic acid. This is 1, 2, 3, 4, 5 with an OH, that's pentanol. Put them together, take out the water, and you're going to, what's the alcohol? Pentyl butanoate. And of course, that is apricots, I believe. All right? So I'm just pushing out the water. So this would attach to this side. Okay? Example, 1, 2, 3, 4. 4 is butanoic, pentanoic. 1, 2, 3, 4, 5. And this is 1, 2, so this is ethanol. They come together, the water comes out, you push them together, and you can see that this is going to be ethyl pentanoate. The ethyl part comes from the alcohol, and what you do is you split it down the middle. Split it down the middle, and you'll see the alcohol part's here, the acid part is here, and of course the water. It's a dehydration, and we call it esterification. And it's the apple flavor or scent. Okay? Now, when you get a compound, split the double bonded C and the double bonded O to figure this out. So here's an ester. Split it. The carbon with the double bond has to be the organic acid. The O had to come from the alcohol. So if this came from the acid, 1, 2, 3, 4, 5, okay, you get pentanoic acid. This came from the alcohol, 1, 2, 3, that's propanol. And the naming is, well, the alcohol gets the YL beginning, so propyl pentanoate. Fruity smell. Try this one. How would I name this one? Again, split it down the middle. There's my, what side has the double bonded C? That's right. Well, there's the alcohol side, so this is the acid side. And the alcohol, it's a hexanol, butanoic, hexylbutanoate. All right, here are some examples. And I have the answers, you can go through them. Look at this one, propyl methanoate. Propyl, because this is the alcohol part. Why? Because the double bonded part belonged to the acid. The acid part gets the OAT ending. Methanoic acid becomes methanoate. Look over here. This is ethanol. So ethyl propanoate. Okay, look at this one, alcohol side. Meth-eth-pro-butanoate. So methyl. Methyl is the alcohol part if I cleave this. Methyl butanoate. Okay, and so forth. And you can click through to go over that. All right, and there's some sample problems here. All right, so no, this was a long one, but please go through and click through and name these, and also now go through the assigned workbook numbers that I gave you.